Good morning, everybody. Thanks for joining us. I'm Kevin Renaud with Peerless. Today we're going to be discussing the emerging trends, valves for hydrogen and carbon capture. There's still some people trickling in, but they'll be certainly able to view the recording once this is over. So first, just a little bit about us, because we do know there's some people attending today that might not know about Peerless. So real briefly, we did open up in 1914 downtown Buffalo as a general mill supply company. Back in the heyday of the Erie Canal. And we've adapted and evolved many times over the years because we've had to now become a trusted source for process components that both keep plants operating efficiently and projects running smoothly and on time and under budget. So we operate under three primary segments. We have our process division, and this would be really working in the plant environment, helping the plants keep running smoothly. Kind of the MRO side of things. We also have our Procore division, which does focus exclusively on OEMs, equipment builders, packagers, EPCs, and some capital expense projects. And finally, we have our high temp fabrication division. Many of you may not know about this one, where we work with scientific surfaces, high temp insulation, doing a lot of laboratory work. So real quick, I am Kevin Renaud, as I mentioned. We also have Dave McHenry joining us. He's going to be behind the curtain. And if you look at the panel, you'll see so you have an opportunity to raise your hand or to chat a question. He will be monitoring this, and he will jump in if he sees a question that needs attention. And also with Oliver Valves, we have Nick Howard, the engineering director of Hydcovalves, and Rob Porter, the sales manager. And we'll get to them real shortly. Briefly, Oliver Valves started in the 70s with a new concept on a non-rotating tip for a needle valve. That technology that was patented is still used in all of their needle valves across the range, incorporating in their double block and bleed valves. And certainly today's topic is their Hydcovalves division. We're super pleased that Oliver has decided to get on board and really be a part of the solution for cleaner energy, and we're thrilled to be their partner for this. And one of the reasons why is the amount of projects globally. You can see the carbon capture and storage projects going on globally, US leading the way, and here are the hydrogen projects going on. And again, Australia is by far away ahead of everybody, but we're not far behind. So with that, I'm going to turn off my camera and turn it over to the gentleman from Oliver Valves. Once again, thanks for joining us.
Good morning, folks. Kevin, can you hear us okay? Are we live?
You are live.
Perfect. Well, look, thanks, Kevin. Really appreciate the introduction, and also to the Peerless team for inviting Oliver's on this opportunity to present, and give an overview of the Oliver Valves business in general, but also predominantly with Hydcovalves being the main focus really for this discussion. As mentioned by Kevin, my name is Rob Porter. I'm the sales manager for Hydcovalves. I've been with the business now for approximately 17 years in different areas of the business, but predominantly sales. I've worked in the oil and gas industry for some 30 years. And this is my colleague, Nick.
Good morning. I'm Nick Howard, the engineering director. I've been with Oliver's now for 18 years now. Started as the sole R&D engineer, and then moved through the business, became engineering director about 3 years ago, and I'm heading up the engineering side of our new venture, which we're here to talk to you this morning.
So just giving a brief outline for the company, so as everybody's aware who we are as a business, Oliver Valves. As Kevin mentioned, we started in 1979. So we've been in operation for over 40 years with a manufacturing base in Knutsford in England, with a further 4 offices globally. We've got one in Scotland, one in the Middle East, one in the Far East, and then we support the market with a strong database of strategically placed distributors globally. And that supports our target markets such as oil and gas, petrochemical, chemical and refinery. Throughout the proud history as a business, we've always strived to deliver and develop progressive technologies, always aiming to leverage and support the industries in which we operate. Our thirst as a market leader has resulted in the introduction, really, of 3 further businesses. So we have Oliver Hydcovalves, producing products suitable for subsea applications. We have Oliver TwinSafe, producing the pipeline products, and then most recently we have Oliver Hydcovalves, and we're producing valves predominantly focused on technologies for this sustainable future. So we really are the green side of the business as we move on. So giving you a very brief outline of the business and the products that we manufacture, as Kevin alluded to earlier on, we started business producing needle valves, predominantly for topside applications such as needle valves, manifolds and ball valves. And then through several collaborations with key end users, we advanced our technologies further, and that really introduced to the market the first true double block and bleed valves. And we see Oliver as the first person to deliver that to the market. Some years later, recognizing our strengths as a progressive engineering company, we're engaged again by another end user to deliver a range of subsea valves. And that now, as a business, produces gate valves, ball valves, needle valves, all suitable for those subsea demanding applications. The natural progression for the double block and bleed valves was to move that from our smaller sizes up to 2-inch to Oliver TwinSafe valves, producing valves up to 18-inch, whether that be full or reduced bore double block and bleed valves for pipeline applications. Whilst we do double block and bleeds, we often sell these now as single ball valves as well. So, recognizing the global concerns and issues that surround the traditional hydrocarbon market, such as global warming, zero emissions, we've now recognized that there's a need for the 4th business in Oliver Hydcovalves. This business specializes in the production of valve technologies specific to these hard-to-abate markets. So, aimed at supporting net zero, reducing global warming, and the definite transition away from the traditional hydrocarbon markets. We fully expect that it is still going to be a big part of Oliver's business, the traditional hydrocarbon markets. But the transition has to be made away to these greener opportunities, let's say, to clean energy. So as we move on to clean energy, recognizing that decarbonisation, sustainability and green energy are now expectations of all governments, the general public and the global energy sector, that sector is now facing a major transition away from those traditional fossil fuels. Significant growth in areas such as renewables, producing wind, solar, but these really are heavily reliant on storage to meet demands of the modern world. We simply don't have that in abundance at the moment, this storage facility. So we see that as a gap in the market. Recognizing that all energy end users are unable to convert to electric, we see that hydrogen is key to that global future, with end users who have existing heat or high energy who can convert to hydrogen or other bio and synthetic fuels with ease, really. Hydrogen seems to be the natural choice just at the moment. It's abundant, clean burning, has high energy density, and we're able to produce that cleanly, best of all. With global demand for hydrogen increasing, we're now starting to see a real thirst for hydrogen in the market. And as Kevin alluded to on the slides there, the number of projects that are starting to move globally is really stepping up now. And whether that's blue, green, pink, grey, the spectrum for hydrogen now is growing rapidly. It really is. So, what we aim to do is to aid that transition away from fossil fuels by supporting valve technologies for those markets.
I mean, it's fair to say we're seeing some hybrid projects as well, aren't we? Which are taking, you know, other green energy methods such as solar and wind and combining those with hydrogen and almost using the hydrogen as a sort of a battery, a way of storing energy. And we're seeing that globally, it's fair to say, isn't it, Rob? We're
Absolutely,
seeing a lot
yeah.
of that sort of information.
Yeah. So onto hydrogen specifically. In Hydcovalves, we're utilising our extensive history and world-recognised R&D facility to produce a range of valves that are specific to this market in technology, materials and construction, which will transition all the levels of industry, whether that's subsea production, topside pipeline valves, and topside instrumentation products. We feel that we're well placed. We can produce gate valves, ball valves, needle valves, manifolds, double block and bleeds, single isolates, all specific in design, materials and testing to cover both low and high temperature applications, along with low and high pressure applications specific to hydrogen. In the carbon capture market, similarly to hydrogen, we've leaned on, you know, all that years of expertise and knowledge to develop further products, and we've ensured that we have a capable range to cover that carbon capture market. So with existing supplies of gate valves from the subsea to pipeline double block and bleeds and instrument valves, we really do, you know, believe that we're well positioned in the market to cover carbon capture and hydrogen applications, which to us delivers a much greener, you know, market.
And we're very aware that the sort of carbon capture market is going to be so cost sensitive. You know, in effect, it's a parasitic cost at the moment. It's until it's heavily taxed, if that's the way it goes, it's really a cost no one wants to pick up. So we're conscious of that. We've got to be aware of how we keep the cost down, but, you know, be able to deliver a product that's reliable and suitable for the application.
Absolutely, yeah. So if we move on through the presentation here, Nick's going to drive now and talk about some of the challenges that we encounter when we consider hydrogen or carbon capture applications. Yeah,
so as Rob's just explained, we're very fortunate. We've got a wide range of products within our portfolio, and these have all sort of derived from solving problems. We've never really had a thirst for just creating catalogues full of different valves. It's more is sort of it's generated through problem solving with customers and end users, and each one of those designs is probably has its own unique set of challenges. And I suppose the same can be said for hydrogen. You know, hydrogen has some unique characteristics that mean not all products, whether it be a valve or a pipe necessarily, or any sort of pressure equipment, is suitable for hydrogen service. So what I wanted to do over the next few slides is share with you some of the challenges we've discovered, some we've overcome, some of the developments that we're working on, and just share with you the knowledge and that we've gained so far with hydrogen applications. So typically, valves are made to be operated in demanding circumstances, and as such are made from high performance exotic materials, duplex, super duplex, high nickel alloys as just a few sort of examples. But these all tend to be or can be susceptible to a condition known as hydrogen embrittlement. Now, hydrogen can absorb into a material structure. It can congregate at grain boundaries, as the image on your screen will show, and these can be either dislocations or even impurities. And what happens when it sort of congregates is it can result in a loss of ductility within the material, and doesn't necessarily affect the yield strength, but can, in worst cases, lead to catastrophic failure of a component. And the two images on the right of your screen there will, one being a ductile impact specimen, but when it was subjected to an impact load, there'll be a certain amount of stretch in the material, to put it in sort of basic terms, before it fractures. The material underneath, very brittle fracture. That image is quite characteristic of almost like a cast iron breaking. There's no give, it just sort of ultimately fails at quite a low impact strength. And that's really the challenge of material selection. Hydrogen can cause a material to behave in quite a brittle manner. Now, to have hydrogen embrittlement, you effectively need three things. You need the presence of hydrogen, which obviously for this discussion is pretty obvious. We need a stress or a load, which again, for a pressure retaining component such as a valve is going to be inevitable. But you also need a material that's susceptible. So take one of those points away and you can safely move away from hydrogen embrittlement. So our approach is to use a material that's not susceptible. So we've standardized our range on austenitic or super austenitic stainless steels, such as 316, widely used in the industry, but well known in metallurgical terms to be not susceptible to hydrogen embrittlement in most cases, which we'll talk about later. But this, in effect, can cause a challenge in itself. It's not simply a case of swapping out all materials for austenitic. The exotic high-performance materials are often selected not only for their corrosion-resistant characteristics, but also their superior strengths. And inherently, austenitic materials are weaker. So changing out for a weaker material causes a challenge in itself, and it's not necessarily a case of just making things bigger. So various challenges associated with material that we've all got to be very mindful of. So polymers and elastomers are often used to create seals within components within a valve. So typical materials could be PEEK, PTFE, sometimes graphite, and as I'm sure you're aware, a whole host of elastomers. But gases can permeate through polymers and elastomers, and the rate at which they permeate, or their permeability, is dependent upon a number of factors: temperature, pressure, and also the size of the gas that's being tested. Now, hydrogen, as I'm sure we all remember from a chemistry lessons, is a very small molecule, and therefore has the ability to permeate through seals at a faster rate than with testing with nitrogen or other gases, either from a test perspective or from an application. Now, here, helium, very similar size molecule to hydrogen, and is often used for seal testing, certainly in fugitive emissions, and has very similar permeability rates to hydrogen. But from a sealing aspect, it behaves quite differently. So two different sides there, there's permeability and sealing, and often confused but between the two, but they do behave in quite different manners. Now, I'd just like to talk a little bit about a case study. Olivers were approached by a well-known oil and gas operator in the UK to come up with a high temperature application for a refinery in the UK. Now, this was for the specification called for an extremely low fugitive emissions rate, but at a high temperature. Now, fugitive emissions is well known, and a lot of experience with fugitive emissions, certainly over the last 15 years or so. But up to, say, 200 degrees C, so 390 Fahrenheit, it's fairly easy with conventional PEEK or PTFE seals. But when you get to 350 or 660 Fahrenheit, you therefore need a new seal, because convention would normally suggest you use a graphite. But graphite's not overly good, or in fact pretty terrible, from a permeability point of view and fugitive emissions. So we worked very closely with DuPont and came up with our own high performance composite polymer that had pretty stable, or very stable mechanical properties right the way through the temperature range of the project. So -50 to +350 degrees C. But this material was new to the oil and gas industry. It wasn't recognized by the end user. So there was a challenge in itself of not only qualifying the valve, but actually getting acceptance from the end user. So using our own in-house R&D facilities, we managed to demonstrate its performance through our own range of qualification tests and gained acceptance from the end user. We also patented the idea, and then later found that actually this was tested with helium, and as mentioned earlier, there's very similar permeability rates to hydrogen, and is perfectly suited to hydrogen applications. In fact, just to give you an idea, the permeability rates of the material we were using is about 100 times better than conventional PEEK seals. So not only could we do the temperature range, but this gave us a perfect solution for hydrogen applications.
After all, really, the valves that we're talking about, the primary focus is for them to be isolation valves.
Correct.
And
yeah.
our speciality really is giving or de-risking those customer applications, making sure that they have, in soft seated valves, zero leakage. And that is the whole goal of this. And, you know, to have a range that is capable of -50 to +350, we don't see as there's many manufacturers out there who have the certification or capabilities to do that with the zero leakage as well. So, you know, through Nick's design and hard work with the team there, it's a real top level product for us to have in this, and it fits perfectly for hydrogen.
Certainly. And, you know, we go to great lengths to make sure that you know, there's zero leakage. And when the environment in which they operate in gets really difficult, operators tend to suggest or specify metal to metal sealing. Now, metal to metal sealing's nothing particularly new. Oliver's been using metal to metal seals for certainly the last 20 years, mostly in its gate valve applications. But achieving a leak tight metal to metal seal on a flat surface, such as a gate and seat, well, it's actually fairly easy. And I don't mean to offend any gate valve designers amongst you, but the real challenge is when you try and do that on a spherical surface, such as a ball valve. When a ball valve is under pressure, it will deflect. Now that deflection causes a challenge because it doesn't deflect uniformly. The geometry of the ball, in effect, is asymmetric. Because you've got the hole through the ball, you've got varying wall thicknesses around where the sealing land is. Now that can be a challenge in itself, and is often addressed using the right material, strengths of material, and the geometry and size of the ball. But actually, the real magic, and the bit I want to share with you today, is actually in the tungsten carbide coating itself. Now, tungsten carbide coating is used to create a nice hard wearing surface, so the components can operate against each other without causing any issues. But porosity within the coating, we've learned, is the difference between a standard metal seated valve and a zero leakage reliable valve. So we set out recognizing this, and we work with various tungsten carbide suppliers, more around the world, well-known manufacturers, to set out to create a non-porous coating. Now, the first thing we needed to do is come up with an easy way of testing if the coating is porous or not. So the images you'll see on the screen there, they're from a ball that's actually failed our test. and has been pressurized in a pressure vessel for about 30 minutes using helium. It's then been taken out of the pressure vessel and put in a water bath. Now, any bubbles emitted from the surface indicate porosity. Now, if you were to wipe your finger across those bubbles, they probably return within sort of 5 or 6 minutes. Now, this poses a real difficult challenge because within a ball valve during a pressure test, you can't see if that porosity is actually through seat leakage or is just porosity. So we set about trying to come up with working with suppliers to create a non-porous coating, and only one supplier could achieve the standard we wanted. Using this test method, they were able to test out on an easy sort of production batch method and achieve zero leakage. And what we've done since this discovery is not just testing 1 or 2 valves. This is through a whole range from sort of 2-inch right the way up to 10-inch, I think we've got. And it's not necessarily zero leakage through a factory acceptance test where your valve might get operated 2 or 3 times. We've actually proved this through hundreds of cycles and at different pressure classes. So again, perfectly suited to some hydrogen applications. Certainly some of the pilot schemes we've seen where industries are moving over towards the use of hydrogen, such as cement manufacturer, where you need a valve that will be capable of dealing with abrasives, but also would remain zero leakage with a hydrogen gas. Now, I want to talk a little bit about industry standards because we all love a good standard. And
we're awash in the market.
Yeah,
Certainly the oil and gas market is
sat
awash
there
with
in the
a number.
evening reading your favourite standard is common practice. But there are a number to choose from, but they all tend to be adopted from old or new oil and gas standards, and mostly they're in their infancy in terms of hydrogen applications, which is quite strange, really. You know, hydrogen's been used in industrial applications for hundreds of years, but there doesn't really seem to be anything that's relevant to a hydrogen valve that's needed in the market now. So, you know, external leakages using helium are covered in the ISO 15848 standard, well known, and actually was part of the previous case study we mentioned. And this seems to be the go-to specification from a qualification point of view, and also in terms of making sure production valves are suitable. But is it enough? You know, does it really suit what operators needs? You know, because if we think about it, the real reason of a qualification is to make sure it's suitable for the application. It's almost a show, it's like a guarantee of valve performance. Now, we have certainly been hearing from pilot schemes that there's not really a go-to specification that meets their needs. So what we thought was we'd actually write our own. So with any new product, we tend to look for the most arduous specification that suits the application.
If that's, sorry to interrupt there, if there's a situation where there isn't a specific test, and that's what we're finding, what Nick has alluded to there is what we're finding at the moment. If we're seeing inquiries, we're not seeing end users saying, no, I wanted testing to API 598, I wanted testing to X.
They're saying, what do you want? What do you recommend?
What can you recommend? And that's where Nick's, you know, coming to as this point.
And it's in complete contrast if you think of like the subsea industry, subsea valves. And whenever we designed a new subsea valve, we'd look at what's the most difficult qualification that this product's going to see. So we you know, it used to be the Total spec that had everything in it: cycle testing, stepwise testing, see, you know, every test you could think of under the sun. Well, why don't we just use that approach with hydrogen? So what we did was we looked at various specifications from subsea, pipeline, instrumentation. We even looked at hydrogen transportation. Thought, right, where are all the relevant bits that are going to be useful to an operator for a hydrogen application? And we thought, if we can come up with this procedure, it's going to safeguard us for the future, but also be able to predict where we think the market's going to go. So we called this our gold standard. We've included seat tests with helium because, after all, you know, we sell isolation valves, as Rob was saying before. You know, they're used to isolate a media. In this instance, hydrogen's the media. So let's test it in an isolation scenario. External leakages with fugitive emissions, measuring with a mass spectrometer, you know, is a no-brainer. That's in there. Secondary stem seals. You know, this is something we've learned from subsea, really. If you've got two stem seals within a valve, we'll independently check them. You know, independently prove that one's as good as the other, or else there's no real point in having a second one, is there? Valve signatures. Now, I love this. This is basically a method of being able to prove that your prototype is just as good as your production valve. So within the qualification, you'll measure or record, should say, the unique characteristics. So inlet pressure, outlet pressure, body pressure, against whatever you're operating at. So if it's against torque or hydraulically operated. And what that creates is a sort of unique footprint or signature of how that valve performs. Now, if you record those through your qualification, you can see if the product has improved or is in essence degraded. But what it also allows you to do is to be able to benchmark every production valve against your prototype. And you can set criteria. It's a really, really brilliant tool. Rapid operation. You know, we're often asked to provide actuators with valves. Well, if it's going to have an actuator, let's do the full qualification test using that actuator to simulate in-service speeds. Now, once we've completed all these tests in-house using helium, we then thought, well, yeah, helium works very similarly to hydrogen, but we want to be 100% sure. So what we've then done is taken this and had it verified by a third party using 99% hydrogen. And this all amounts to basically the base point for all new products.
And ultimately, what Nick is alluding to there is what we see in the market at the moment is a real gap for hydrogen valves. What we see with competitors' valves at the moment is lots of people that are happy to sell a ball valve without too much testing or qualification to say, yeah, it's stainless steel, it's good for hydrogen. But what we are really seeing is, with the depth of testing that we've done and the findings that we have, is we want to be testing with hydrogen. It's very different. It's proved very different results. So
yeah, and that's echoed by the seal manufacturers. You know, at the moment, a lot of seal manufacturers are doing their own tests. You know, they're testing peak, PTFEs, O-rings, and what they're seeing sort of mirrors what we're seeing in testing. Is permeability wise, yeah, it's similar to helium. You know, you can, should we say, you can draw some parallels performance wise testing with helium versus hydrogen. But from an isolation point of view, from a sealing point of view, hydrogen moves a lot faster than helium. You know, if you ever do a test with helium, it's quite sticky stuff. You know, it's difficult to get rid of. Whereas hydrogen's the opposite. It's hard to contain. It dissipates so fast that actually sealing it within something is quite a challenge.
Yeah.
So some of the things we've been working on it, testing to our gold standard, and we've had that verified by a third party in Germany. And we're both very proud to say our ball valve was the first valve that's been qualified by TUV worldwide. TUV have been fantastic working with us. They came over to present us with a certificate because we were the first actual product, actual pressure retaining valve to be tested on hydrogen. We're also looking into some transportation products, isolation valves for hydrogen dispensers. And what's involved in that is 102,000 cycles. And we've completed that, but crikey, what a learning curve. You know, historically, 2,000 cycles was a big test.
Well, we can't say enough, really. Nick's saying 2,000 tests. If we completed a valve on an oil and gas application, there's very limited applications where you need 2,000.
Yeah.
They're very much reduced in regards to cycles required for the transportation valve for a valve to be cycled in as many times as 102,000 cycles. It's just unheard of for a valve that we've manufactured.
And that at the end of 100,000 cycles were at ambient, 2,000 were at temperature. So 1,000 was at maximum temperature, 1,000 was at minimum temperature. At the end of that, it was fugitive emissions tested. That's not high. It's not needed in the spec, but we did it for our own information. And it was within leakage rate B to the ISO spec. And seat leakage wise, we're at zero leakage. But it's just opened our eyes to how a valve performs over that sort of number of cycles.
Yeah.
You know, you're into the actual wear of a seal. You know, after 2,000 cycles, we'd expect a valve to come apart and look the same as it did at the start. But 102,000, we've learned a lot.
Yeah.
So,
the other point to note is for that valve, for the application and specification, that specification doesn't need a cross-seat leakage test.
No.
It wasn't concerned by the valve passing or failing through seat leakage. It was simply via the seal housing, wasn't it?
Yeah.
But the testing that we've done and the integrity of the product that we produce allows us to do 102,000 cycles and guarantee zero leakage across the seat, which we believe is critical for an isolation valve that we manufacture.
Certainly. And you know, another one, using our sort of metal seated pipeline developments, we've completed 410 cycles with zero leakage on a metal seated valve, both trunnion and floating designs. The 410 comes from the next endurance category of the ISO spec, but we've made a bit of a hybrid spec in that we've added in seat tests. We're also developing a 3-way pneumatically operated selector valve for TUV. We were approached not only to offer the product, but because we had the facilities to test a valve that could operate at the speeds that they wanted. So this valve is to be used on a metering skid, so it needs to be able to switch between directions in effect within 0.1 of a second. Now, operating a valve 0.1 of a second is fairly commonplace if your actuator's fast enough, but we've got facilities to actually measure and take readings within that operation. So we can measure it 100 times a second. What that gives us is a lot of data that we can use to analyze how the valve's performing through a number of cycles. But again, quite a unique challenge, that one. We're also looking at a full range of austenitic subsea valves, up to 2/16 API sizes, but perfectly suited for subsea hydrogen storage, which we're seeing a growing need for within
Absolutely, yeah.
the market.
whether that's hydrogen or carbon capture. You know, again, as we mentioned earlier up front, those gate valves are used in both of those applications.
Yeah. So, so what does the future hold? Well, imagine you could have a range of lip seals that were 100 times less permeable to hydrogen than PEEK. Now, we can produce lip seals that are made out of materials that are less than 100 times permeable to hydrogen. We're looking at a full range of austenitic subsea valves, whether it be gate valves, needle valves or ball valves, all rated to qualified industry standards at 3,000 meter water depths. Advanced subsea simulation. We're very proud of the fact we develop not only the products themselves, but the way in which we test them. You know, for us, it's part and parcel of the product. You know, you've got to be able to test it, to simulate as close as you can to real life scenarios to prove that its performance.
And that's in-house testing, we have to say as well. You know, the R&D facility where Hydco are currently situated, we have all of that capability under one roof. So Nick works very closely with the R&D team to ensure product is tested to suit those applications.
But I suppose really one thing I wanted to end on is, you know, we despite all the qualifications and testing that we do, probably our greatest lessons learned, a collaboration of ideas with customers and end users, and that collaboration of technologies and discoveries we feel is really at the heart of where the green energy sector is going to be. And you know, our goal as a business is really to be right at the heart of all that development.
Yeah. Those collaborations have been key to Oliver's success in the past with both twin safe and subsea applications. We've always thrived on those challenges. So any end user out there who has a challenge for carbon capture or hydrogen, those are what we thrive on. And you know, we're not just delivering very basic valve technology. We want those challenges. Bring those challenges to us, and we'll deliver that valve technology.
Well, yeah, we'll work with you and help solve the problems. So.
Absolutely. Yeah.
Thank you very much for listening. And
we can turn that back over to Kevin and the team at Peerless to see if any questions have been generated.
Dave, do you have anything for us?
No, at the moment, there's no questions. I think the content was covered really well. So while we still have the folks from Oliver, if anyone does have a question, whether they send it through the panel or if they raise their hand, I can unmute you if you had a question, let me know. But I think at the moment, we've covered the topic really well. Thank you.
Thanks, Oliver, for supporting us here today. Thanks for everyone that joined us today. Again, if there are any other questions, we'll take them through email or phone calls anytime.
Absolutely.
We do have one question that just came in. Bear with me. I'm trying to unmute you, sir. One moment.
I have one question.
Yes.
Is gold plating helpful in hydrogen permeation?
sorry, gold plating, did you say?
Yes, gold plating on SS316. Does it help in preventing hydrogen permeation?
It's not something that we've come across. I know that gold is pretty inert in terms of hydrogen, but gold plating the components not something we've heard about or had any dealings with.
Yeah, right? But perhaps we would think of it along the lines of traditionally it being a very soft material that the valve operation, the components that we talk about, we probably would not lend themselves to that form of coating really. if we're talking about metal seat technologies, traditionally they need to be harder technologies than I think that than what gold would provide. Yeah.
Okay, thank you.
All right. Thank you for your question. And as Kevin said, if you do have any further questions, feel free to send us an email and we will respond as soon as possible. Thanks everybody for your time today. Thanks, Kevin, Rob, and Nick. Well done.
Thanks for listening.
Thank you, everybody.
All right, bye now.